Hey everyone, welcome back to Deepia. In this video, you will learn how autoencoders transform complex data into a simpler, more meaningful representation, called the latent space. With the first papers published 15 to 20 years ago, autoencoders laid the foundation for much of what we see in modern deep learning. They form the backbone of popular architectures such as U-Net, which are widely used in various image processing tasks. Even cutting-edge generative models such as DALL-E or Midjourney are built on the principles of autoencoders. So let's start with the basics. What is an autoencoder and how do we train it? An autoencoder is a type of artificial neural network used to learn efficient representations of data. This means that the model tries to describe very large data with as few features as possible. To put it more simply, imagine you're trying to describe someone to a friend. You could start by describing their hairstyle, their height, their age, or the color of their skin. In the end, you might decide to describe someone with just two numbers, their age and their height. It may not be the best representation, but it is certainly a very compact one, as it is only two numbers. Autoencoders do essentially the same thing, but for different data. The basic architecture of an autoencoder consists of three main components: the encoder, the bottleneck or latent space, and the decoder. The encoder compresses the input data into a latent space representation. This latent space is a low-dimensional space that captures the essential features of the input data. The bottleneck layer, which is the smallest layer in the network, holds this compressed representation. Finally, the decoder reconstructs the input data from the compressed representation produced by the encoder and the bottleneck. Instead of this simple 4D data, an autoencoder can also compress much higher dimensional data, such as tabular data. Another very common example is encoding images such as this picture of a rabbit. The encoder reduces the image to a few key features, the bottleneck layer holds these features, and the decoder reconstructs the image from these low-dimensional features. Now let's see how we train such a network. Training an autoencoder focuses on minimizing the difference between the original data and its reconstructed version. The goal is to improve the decoder's ability to accurately reconstruct the original data from its compressed representation. At the same time, the encoder becomes better at compressing the data in a way that preserves critical information, ensuring that the original data can be effectively reconstructed. But how do we measure the difference between two images? Well, the simplest way to compare two images is to compare each pixel individually. For example, we can calculate the difference between corresponding pixels and then take the average of these differences. This method is called the mean squared error, or MSE. As the name indicates, each difference is squared to ensure all values are positive and easier to work with. This gives us a single number representing how far apart two images are. During training, the autoencoder learns by trying to reduce the mean squared error for each image it processes. We won't dive into the details of this process here, but Grant Sanderson from 3 Blue 1 Brown has an excellent series of videos on this topic. Here's a typical training scenario. At the beginning, the reconstruction error is high because the autoencoder's weights are randomly set. As training progresses, the error decreases, and the autoencoder gets better at accurately recreating the original image, which now looks almost identical to the input. Now that we have a basic understanding of how an autoencoder learns to reconstruct images from their latent representation, let's explore why we use such models. As we already mentioned, one of the main advantages of autoencoders is their ability to perform data dimensionality reduction. The dimension of the latent space is determined by the number of neurons in the bottleneck layer. For example, if there are 2 neurons in the bottleneck, the latent space is two-dimensional. This allows us to visualize how each data point is encoded by treating the activation of each neuron as a direction of a plane. If the first neuron is strongly activated, the encoded representation will be on the right of this plot. And if the second neuron is activated, the latent representation will be at the top. Let's consider instances of the number 7 and their latent representations. If the autoencoder is very well trained, each instance of this number will go in the same region of the latent space. Now, if we encode instances of a different class, for example the number 4, These instances will also form a cluster. Again, in an ideal situation, this cluster is supposed to be far apart from the cluster of other classes. What happens is that during training, the latent space becomes sort of organized, with each class occupying its own distinct region. Let's have a look at how the latent space actually evolves during training. We take a set of latent representations that will be plotted at each epoch. You can see that clusters start to form and latent representations move around a lot during this early training phase. After a few epochs, as the training converges, the latent representation does not change anymore. Although not perfect, this organization of the latent space already makes it much easier to work with the data. For example, a classification algorithm such as nearest neighbors would probably give a decent result on this representation. An important choice in the design of autoencoders is what we call the latent dimension. This is basically the number of neurons at the end of the bottleneck, and it is the most important part of the network. We call it the latent dimension because the data is encoded with as many numbers as there are neurons. So if we have 2 neurons, as we saw before, the data is encoded with 2 coordinates on a 2D plane. If we have 3 neurons, the data is encoded with 3 coordinates in 3D space. And if we have even more neurons, the data will be encoded in 4D, 5D, or even higher dimensional spaces. In the following examples, we trained each network exactly the same way, changing only the latent dimension. As you can see, if the latent space is too small, the autoencoder may struggle to identify essential features of the data. This ultimately results in poor reconstruction quality even if the network is trained for a long time. Even with a 2D latent space, the reconstructions are not always accurate. As you can see, this 4 becomes a 9. But if we take a larger latent dimension, the number is reconstructed correctly. You might ask why we care so much about the quality of the reconstruction when all we want is a nice latent space to work with. The thing is, poor reconstruction quality often translates into poor latent space organization. With a 2D latent space, we saw that the reconstructions were not that good and the latent space was not very organized. We can see some clusters, but they overlap and are all in the same region of space, and some of them are very sparse. For instance, the cluster of zeros. If we switch to a 5D latent space, we can see that the clusters are much more separated. We can clearly see that the 1s are mainly in the upper right corner of the space, while the 2s are roughly in the middle, and the 7s slightly to the right. By the way, how is it that we can visualize such a 5D space with a 2D plot? Simply put, we project the latent space to keep only the 2 most important dimensions. If you want to know more about how we visualize high-dimensional latent spaces, remember to stay tuned for the next video. Now back to the topic. Even with a 5D latent space, we still have relatively sparse and diffuse clusters. For example, this image of the number 2 is encoded near a cluster of 9s and is therefore reconstructed as a 9. This image of the number 3 is also poorly encoded, resulting in it being reconstructed as an 8. Now that we understand how autoencoders work, with the latent dimension being one of their key parameters, let's look at some real-life applications. So far, we have only seen examples of autoencoders trained on handwritten digits, but of course we can perform classification tasks on any other type of data. Suppose we're in a busy hospital that sees millions of patients a year and probably performs hundreds of thousands MRIs. We have access to the brain MRIs of several patients, but the information about their gender has been lost in the processing of their medical data. But for many conditions, it is very useful to know a patient's gender in conjunction with other information such as their age. And it's very difficult to tell the gender of a patient just by looking at an MRI scan of their brain. In fact, even experienced practitioners can't do it. Fortunately, we can actually train an autoencoder to recognize a patient's gender from their brain MRI alone, based on their latent representation. The autoencoder will represent the brain MRIs in a lower dimensional space, where it is easier for us to identify the gender of the patient. Here we can clearly distinguish the men and the women based on the latent representation of their brain. While autoencoders are used everywhere, they are rarely used in this simple form. Let's see where they're limited. Autoencoders' greatest strength is also their greatest limitation, latent space. If we rely only on the reconstruction loss of the autoencoder to organize the latent space, we often end up with passable representations. As we have already seen with handwritten digits, clusters are not as well defined as we would like them to be. Another noticeable problem is that when we take 2 points in the latent space, we expect that if we take a point in the middle, it will be a mixture of the other two. Unfortunately, this is not the case. Taking such a middle point results in nonsense for most of the intermediate points. Here the interpolation of a 0 and a 6 is a 5, while there are no encoded 5s anywhere near. Finally, autoencoders also learn many irrelevant features. So much so that if we add a bit of noise to the input, the autoencoder won't be able to reconstruct it at all. Here you can see that the reconstruction is getting so bad that the numbers are actually changing, with a 4 and a 5 becoming a 9. This is why most modern implementations of autoencoders regularize the latent space. The most famous type of regularized autoencoder is called a variational autoencoder, or VAE, which will be discussed in detail in one of the next videos. Thank you so much for watching this video. If you enjoyed it, please like and subscribe to help me grow the channel. See you in the next video.